YouTube contains a significant source for flow visualizations of mixing or flow visualizations to help you understand the physics of going on. This one is a very old video, so I wish to use it to demonstrate several aspects here. This was developed by the National Science Foundation a very long time ago, in 1960s or so. And this particular chap is G.I. Taylor. He's at Cambridge University in the 60s. Very famous fellow, very talented person. And quite frankly, it's intriguing what he's showing you here. Okay. And very, very enlightening.
Surface, which must be transmitted through adjacent layers of the honey. The stretching of the stream as it leaves the knife gives rise to tensile stresses across horizontal sections.
Anyway, what we're going to do is just quickly show you the important aspects of this video to the area of mixing. Okay. Now we have a low Reynolds number jet. I'm not quite sure what it is, 0.05 maybe. But you can see the jet entering, very viscous jet entering liquid. And you can see that you have very, very poor mixing going on. Reynolds number 0.05. The Reynolds number is the Reynolds number of the jet up here. And so moving right along here, you have a Reynolds number of 10. And the jet comes in at 10 Reynolds number, and you can see that, again, it's fairly poorly mixed. And this is a Reynolds number of 200, and again, a fairly unmixed system. You're still under laminar flow conditions, and still not very well mixed. And this is a Reynolds number of 3000, and you can tell that there's substantial mixing going on. So this is a comparison between mixing in turbulent flow and mixing in a laminar flow, and why it's very important to understand your process physics. Right. Stop right there. No mixing here, very poor mixing here, and here, very excellent mixing in turbulent flow. 0.05 Reynolds number, I think this was 10, this was 200, and this was 3000. Anyway, some other interesting items in this video is here you have one cylinder inside of another cylinder, and you have a viscous material, fluid in between. And in that viscous material, he's going to add some coloring there. Okay? And the first thing you want to recognize, he's turning the inner cylinder, the outer cylinder is stationary, and the red dye blob has been spread out. And you can assume that it's been mixed in, or it looks like it's been mixed in. Now he's going to reverse it, and it's kind of interesting what happens here. And we'll let you see. So it was mixed, or appeared to be mixed, but then you could reverse it. Completely different behavior. This is a very important situation in engineering as well, as demonstrated by this experiment here. He's basically built two devices. One that's like a propeller, basically goes back and forth and pushes the boat forward, much like perhaps a fish. However, when a snake moves, it sort of pushes off itself, or pushes off liquid near its body, and it propels himself forward. The physics of snake swimming is different than the physics of fish swimming. The point of the matter is shown here. He has a turbulent device, right, with the rudder going back and forth, and that propels the system forward, or the little boat forward, and quite effectively propels the little boat. And he's going to put that in water and show you how it works. And it works spectacularly. However, he puts it in a very viscous system, and it doesn't work at all. So the Reynolds number was changed quite significantly here. And you would have to say that from this perspective, this design is a failure. In a sense, you're using turbulent equipment in a laminar application. So what does work? Basically, he's going to now put in a device that mimics how snakes swim, basically. And you see a very odd device that works a lot better than the turbulent device. So what the point of the matter here is quite simple. You have equipment for turbulent flow, and you have equipment for laminar flow. Turbulent equipment will fail in laminar flow, typically. That's the standard engineering mistake, is that people have a pump, you figure it's going to work no matter what, but a pump won't work. Say it's a pump for water, it probably won't work very well if it's for very viscous molasses. So, very important point to recognize here. Anyway, I'm going to stop that one, and let's see what else we got here. Go surface tension video. I like this one as well. Okay. Oh, wrong one. I hope I bring up... here we go. Part 1. I think this is 30 minutes long, and we have 9 minutes sitting here. We have a gentleman, a very capable gentleman. Again, this is surface tension and fluid mechanics, the speaker, mechanical engineering, Tufts University, I guess that's in, I'm not sure where, Boston, maybe. But he's trying to demonstrate surface tension to you. Very important. He's got a soap film, and you can see that he's creating surface and letting surface fall back. But the very important, striking thing is, well, it's several other examples here. String, basically, and then he's going to put soap in the surface in the middle, and so the fluid outside the ring string is higher surface tension, so it pulls everything out in a balanced way. Here's chem-free boat. Basically, chem-free lets you, one end is dissolving, the other end isn't, so it propels itself. It's really quite fascinating. Anyway, we were talking about simple devices or simple tests to help you understand your process. And I was mentioning that foam is a very common problem for industry, and this could propel itself into a foam meter. You have two glass plates that are separated by a very small amount. You put a little dab of your liquid in there, and you can photograph the behavior of foam, and you can detect differences possibly in foam using this device. You may not be able to put a number on it, or actually you would probably be able to put a number on it. Whether it has any physical meaning or not, it's another matter, but you can certainly rate the foam characteristics here. You have a lot of science going on here. Anyway, why don't we stop with that? See if we can get two here. Here is two capillaries being used. One has a higher surface tension than the other. Probably, let's say, water versus alcohol having a lower surface tension. We won't go necessarily into the breaking of liquid sheets, but let's go on and see what else do we have here. What I really wanted to show. Oh, yes. That might be interesting. One way you change surface tension is by changing the chemical composition. So here we have a ball of cotton that has alcohol in it, and it's affecting the stream of water. And basically, you also can affect surface tension by, well, this is another example of pretty much the same thing. Oh, sorry. Let's go back. You can see wine tears here. That's a surface tension phenomenon. Let's go on. Wine tears. This is a fantastic example of surface tension versus charge. And what he's done, he's put mercury in here, put water and a chemical, some sort of chemical. And then he's basically making a battery. It's got probably an acid of some sort. And what's extraordinary is to realize that surfaces have forces acting on them. Okay. And so you can see that the mercury is moving. Okay. When it gets touched by the nail. The circuit is complete when it's touched by the nail. But you can get it arranged in such a manner that it becomes quite remarkable in what it can actually accomplish. This it's always been impressive to me that you can actually do something like that. And it's being driven by surface charges. Another way of affecting surface tension is by heating it. And you can see heating it. And he goes into a detailed explanation of that. What's intriguing is right here. He has, and this is the point of a very important point in scale up. Okay, this may be a simple item for you. Have an ice cube and an electrical heating plate, but you're sitting there and you say, okay, That's what happens. But you notice the ice cube is rotating. So in process scale up, you really need to improve your capabilities of observation. You may be missing things completely that you should be paying attention to. Again, here you have an electric skillet. It's being heated. The ice cube is spinning. And the question is, fairly simple question is, why is the ice cube spinning? And to solve that would be important to understanding the process physics. Basically, what happens in this set of circumstances is one side of the bubble is heated, which propels lowers the surface tension in that area, and liquid rushes in from the behind and propels the drop forward, so to speak. Here's an intriguing surface tension effect. These are, I guess, acetone on a heated wire. They're very, very small, so you are in a realm where gravity is not very effective. So only when they hit each other do they leave the wire. But I always felt that was interesting comparison of gravity versus other surface forces, i.e. being surface tension. Another spectacular video by the National Science Foundation. There's a whole series of these videos available that you need or should pay attention to. So apparently I may have lost my slideshow. Here we go. And I think we were way, way, way down here. I think. I hope that helped. And I think we were closing in on mixing. Okay. So let's continue on, and we'll finish out this mixing section. Mixing. And why don't we do the slideshow and get my pointer up to snuff here. And pointer color, let's go with blue. And we really need to have a highlighter. And I guess we need to have pointer color, which again are blue. So here we go. Mixing is often center point of piloting studies. Process objective may be mixing. Large-scale mixing, full tank mixing. Large tanks, we've already shown large tanks are more difficult to mix. So what we need to do is talk about mixedness, or the scale of scrutiny as well. What is a desired product? What is considered mixed? And what's the endpoint of mixing? Very important. The scale of scrutiny is the size of the sample going to be taken, right? So here we have what might be referred to as a mixed process. I mean, they're all scattered about. So typically you would think of that as being mixed, right? However, if I take small sections of it, like this section right in here, I see it being fairly unmixed. I have vacant areas here, 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 and no solids in here. Excuse me, no black dots in here. So on the large scale, I'm mixed. On the small scale, or if I look very at small sizes, I'm not. Don't have any mixing. So it's very interesting. You need to tell, anytime you're doing mixing, you got to make sure you record the size of your sample. Right. Then you say you make an addition of concentration or hot water or pH acid, add to a tank, and then you record the reaction at some measurement point. And this being time here, and at some point where it drops to below plus or minus 5%, it's considered mixed. Now, old-time study back 1970s, there was the Dutch people who thought plus or minus 25% should be considered mixed. So here, the thought was in filling operations, the other 25% would take place in the bottle. So effective mixing, no method of addition, no effects of amount added, no effects of location, no effects of fluid properties. So effective mixing are basic engineering starting points for all processes. If you have poor or ineffective mixing, your process objectives are going to be difficult to accomplish, right? You also have the situation where laboratory is well mixed. Laboratory is well mixed, very rapid, results are independent of location, all kinds of good stuff. The plant, however, is notoriously poorly mixed, can be quite slow. May not even mix at all. So in the plant, you could very easily have effects of method of addition, effects of amount added, effects of location of addition, effects of fluid properties. The reason why you want good mixing is the process is simple to model, easily controlled. Production occurs at a uniform rate, and we have quality. You have a uniform quality. Now, what you're after is effective mixing, which is much, much different than procedural mixing. Now, procedural mixing, you have add and stir for 30 minutes. Now, the N theta value might be 40, okay? And if you're going around at 40 RPM and N theta is 40, then you find out the mixing time is 1 minute. So if I have a mixing time of 1 minute, why do I want to stir for 30 minutes? So procedural mixing can be quite excessive. Don't know why this happens, but it happens. Stratification of phases, don't do it. Procedural mixing should be based upon processing need, right? Let's take a look at where this thing came from. Basically, it was tank volume, which would be right as T cubed, divided by pumping, impeller pumping, which is ND cubed. So we have volume, which is length cubed, divided by pumping, which is length cubed per time. So this is going to give rise to some sort of time over here, which we'll write as a theta. Cross multiplying, you quickly find, so this is volume divided by impeller pumping. So you have N theta, and basically you find out that it's some function, some constant times T over D. Remember I said D over T ratio? Here is the T over D ratio. So the N theta correlations typically are written as an exponent of tank diameter to an impeller diameter. And it's not really a third power, but it turns out to be maybe a 1.5, 2.5. Very important point is that the number of revolutions to mix can be quite modest. So if we do a quick calculation, say D over T of 3, A is 2, K is 5, we quickly see that we need 45 revolutions to mix. At 45 RPM, we mix in a minute. Mixing your pancake batter Saturday morning, you're going to make pancake batter. It doesn't take you an hour to make pancakes, right? Pancake mixing is quite simple, quite fast. N theta values may be 30, 50, 100. So you may need 20 revolutions to mix. So you find out that mixing is easy. This is both true for laminar and turbulent mixing. You do not need high speed High speed means low mixing times. That's true. Low impeller speed means large mixing times. That's true. But high speed is not needed for mixing. It will be accomplished. So in industry, you find that there's an awful lot of overmixing occurring in industry. Here's some correlations I just pulled out. You have some Czechoslovakians, you have some Czechs, maybe some Chinese, and you have some people with Delaware. Anyway, you see over here you have just simply geometry. D over T ratio, blade number, blade width effects, liquid height effects. Okay, but it's a function of geometry. There is no Reynolds number. Okay, now down here there might be a Reynolds number poking around. For unbaffled tanks, you have D over T 0.82. A Reynolds number is 1/6. But for the most part, N theta values are constant. Or a function of geometry. Now I should qualify that actually, because N theta will turn out to be a function of volume. So the larger the volume, so it might go up like that. So you need to calibrate your tanks. How do you calibrate your tanks? Well, you go back here and you make a simple addition, right? And you figure out the mixing time. When you make a simple addition, then you come along and multiply by rotational speed, okay? And that will give you revolutions, and then you figure out what volume was in the tank at that time. So you got a data point. You got N theta, you got volume at that time, and then you got one data point. Then you come along, you get another data point. Come along, you get another data point. So you then have your N theta rate values calibrated as a function of volume for different impellers. I mean, different tanks. You calibrate your whole plant that way. Of course, you won't. I was talking about N theta with one company, and they got very enthused. And the next day, when they came back to work, they had 1,000 tanks, and for them to calibrate their 1,000 tank plant, that was tough work. Laminar mixing. Well, here you go. N theta again. This is often expressed as a homogenization number. And it's between 30 and 300. And here we have various values. Helical ribbon, 33. Here's a turbulent mixer in a laminar application. It's inadequate, as we have 65. So we have the Dutch, we have the Japanese, we have some Czechoslovakians, the Japanese again. Up-down mixer, really great. Look at that. 16. Anyway, some Germans, you have the Intermig, or you have the Sigma mixer. You have the Anchor. This really kills me. You got decimal places here. Too much Dutch. This is Czech. Too much Czech beer, I think, huh? It's supposed to be humorous. I gotta be careful here. So you quickly find out that homogenization number is only a function of geometry, as units, the number of revolutions to mix. No major differences between the relationships. That's kind of interesting. They're constant values. In laminar mixing, however, you got to watch out here. There are significant temperature rises can occur. Temperature rises, changes of viscosity, power level, and flow field. Correlations for mechanical mixing in the transition regime. Dash ahead here for a second. Take a look at this. This is homogenization and power number for helical ribbon. Okay, and this is from Czechoslovakian people. Very good at mixing, however. This was during the Cold War. Anyway, so N theta is here. N theta is right here. So if I come across here, straight across, I'll come up with n theta of 60, basically. And in here, I'll come across, I'll get maybe n theta 40. So mixing in a laminar regime, 60. Mixing in a turbulent regime, 40. But in here, we have the transition regime. And you can see that things are not as well, things are not as comfortable as they should be here. Goes up, reaches the bump, and comes back down. I call this the transition bump here. Give it a name. I've seen it, or I've found it in mixing and shaker tables. Yes, some people have studied mixing and shaker tables. Anyway. And quickly you see the n theta value of being 300. So you have excellent processing over here, you have laminar excellent processing over here, and in this region you have n theta value of maybe 300. The other thing you should recognize is maybe you start turbulent and you wind up laminar. So it could be that you're going to pass through the transition regime. So you're mixing very well until you hit the transition regime and you mix poorly, and then you come out of the transition regime as you're getting thicker and you're mixing better. So that's an idea here. Caverns form, they cannot be mixed away. Nagata found that out a long time ago. Japan, 1956. If you got a cavern, I showed you it earlier with the D over T slides, right? With the impeller showing you a cavern and unmixed in a mixed region. So changes in design and methods are needed. This is jet mixing, right? And we have some Fox and Glick was out of Procter & Gamble. We have the Dutch. We have some Japanese, I think, or maybe Chinese. I don't know for sure. We have a few Brits in here. And then you have all these correlations here. This is just a sampling of all the correlations. And you find out that the jet mixing time is basically some sort of volume divided by some sort of pumping. Again, right? Volumetric flow rate, or this is rated as a Q. You have volume divided by flow rate, jet flow rate. Jets mixed by entrainment, right? You do not want to have parallel jets to the wall. Jets will be attached to the wall and can't expand. How long a jet mix stays a jet is kind of an interesting question. Again, you've seen this slide before. And now we'll move on into more interesting situation where we have continuous flow mixing in fed batch systems. Mixing in these things, or in these processes, where you're feeding a batch process, or you have a continuous process. Dominant, you can have several things happening. You can have both jet mixing being very good and mechanical being very good. Or you can just have mechanical being very good. Or you can have jet mixing being very good. Or you can have neither things being worked on. Now, if you examine where mixing is ineffective, well, in a continuous flow system, the material does not have enough high residence time. It doesn't stay in the tank long enough to be mixed properly, right? So it comes in and stays there for a small amount of time, then leaves, and as a result, it didn't get a chance to be mixed in. So you need to have some sort of residence time versus the mixing time. How long is it going to be for the material to be in the tank for it to be mixed? Now that ratio has been quoted as being 50 to 200. That's pretty tough. That's pretty tough. It's got to be in there 50 times the mixing time, or 200 times the mixing time. However, if I was pushing my process, which is often the case in America or in aggressive companies, what you might do is drop this down to 10, 20. In other words, it has to be in there 20 times the mixing time. Volume, the ineffective mixing happens because volume becomes too large. Or counter to that, could be saying the same thing in a different way. The distribution of mixing energy is poor. Volume becomes too large, mixing is too poor. So, mixing time for continuous flow could be mixing time for batch, mixing time for jets. Does not hold for poorly mixed systems. Now, what's intriguing is mixing times are being used to estimate residence time. Right? I already said that 20 times the mixing time might be a good guess for residence time. So you have the residence time, which is 20 times the mixing time, we'll write it as residence time, is equal to volume divided by flow rate. Q would be the flow rate. Tank volume divided by feed rate would be equal to residence time, and the residence time is 10 times the mixing time, right? And the mixing time is gotten from the correlations for the geometry. So you have this mixing time from correlations for the geometry. Correlations for the geometry looks like these, right? These are the correlations for the various geometries, right? Turbulent correlations, laminar correlations. It's usually some sort of n theta thing. So you take 10 times the mixing time, maybe 20 times the mixing time. That will give you the residence time. And then you multiply by flow rate. This is known, typically known, what flow rate. And then suddenly you got tank volume. Now, see, when I was a chemical engineering student, nobody ever explained to me where this tank volume came from. Usually, it would, if you have an example problem worked, it would be, poof, we have this volume. Now, the question is, I can actually determine the volume I need by knowing what flow rate I need and 10 times the mixing time. That will give me a good estimate of tank volume. That's very important. So when I was an undergraduate student and I was faced with this problem, poof, I have 10 cubic foot tank. I mean, that was a very important dimension or quantity to work the problem. And I kept on wondering, well, Phil, where did that volume come from? Anyway, ineffective mixing. Turns out ineffective mixing turns out to be a very complex function of length scales and exponential volume. Ineffective mixing, the volume becomes large, mixing times become exponential of tank volume. Remember, we were saying effective mixing is n theta is equal to a constant. Now, opposite to that, ineffective mixing is when mixing time becomes exponential of tank volume. So when I was doing this work at the time, I had a young child, and I have nursery rhymes for the young child, and I had developed one for the mixing, and it goes something like this. When mixing is good, it is very, very good. And when mixing is bad, it is very, very bad. Or when mixing is bad, it is horrid. I don't know if those nursery rhymes still exist, but anyway. So, when mixing is not effective, method of addition matters, effects of amount added to that matters, location matters, fluid properties matter. Again, a good friend of mine, Don Kessler, he gave me this one also. Recognized Don. Really like that gentleman. Anyway, we have found the three most important effects of mixing on our reactors are feed location, feed location, feed location. Sort of like real estate. processing geometries cause ineffective mixing. Solution is redistribution of power. Some processes are so starved by limited mixing that almost anything can have an effect. Effects are exponential, gives rise to on again, off again. Okay, there's significant overmixing done in industry, and there's significantly poor mixing occurring in industry. So industry has this system. Basically has the worst of both systems. Significant overmixing simultaneously with poor mixing. Here we have a process we were studying. This data was taken by a technician. I didn't do it. Ed Kaiser is a friend of mine down at Savannah River. Okay, and it was done in 1991 when I was down there. And we have a typically industrial process sitting here, which means it's completely poorly designed. Did you catch that? Let me repeat it to make sure you understood. We have a typical industrial process, which means it's poorly designed. Okay? Sorry, I apologize to industry. It's okay. You can handle it. Anyway. So, we have a situation where we have an undersized impeller. We do have baffles along the side walls here. Nope, not along the side walls. It's along through the impeller shaft. This is the only place we could have baffles. They do not want to put baffles on the wall here because of the process. Anyway, so we have A, B, C, and D conditions where there's an external feed jet. Excuse me, the external feed jet was not used, right? This caused poor mixing in the upper corners of the tank. So the feed jet was right here. Excuse me. There was no feed jet. So what happens is we were measuring the mixing time at this volume, mixing time at this volume, mixing time at that volume, mixing time at that volume, and mixing time at that volume. With no external jet, right? Conditions A was where the external jet feed was not used. And basically that means the jet was right here. This was a submerged jet. Right? So there was this feed stream, and this feed stream was mixing. And the impeller was also on, right? So we better go back here. And again, A, B, C, and D, the jet was coming in here, and we have the rotating impeller, right? And we had the jet mixed this very well and mixed this very well, right? But as we raise the liquid level up here, we have a huge dead zone right up in here. So you have a power source here, and you have a power source here, but there is no power source up here. So as a result, you're creating a dead zone. As you continue to raise the liquid level here, the dead zone occurred. Now, E, F, G, and H was where the external jet was used. So this clean up our slide and show that. So the excess jet was coming in plunging down. And what happened, it mixed this area. In fact, what it would actually do was entrain gas bubbles. And the liquid part of the jet continued straight on down, and the bubbles would turn upward and sort of cause motion in this direction. So it's kind of intriguing that this external jet mixed a rather wide volume up here. And down here we still had the impeller on. So again, we have two sets of conditions. These two power sources working, that's A, B, C, and D. One on, one off, both on, right? And then we had this power system working. Erase that. We had this one working with this one working. So the power distribution spread out. So it was well mixed here, and there was cross-mixing between these two locations. The situation here, it was well mixed here, but dead up here. This was dead. Okay. You will also notice, before we look at the data, that we were creating a dead zone up here, and we're changing the power distribution. Most of the power remains in the bottom of the tank. Okay. There was no flow in here. By the way, if you have a dead zone, standard trick would be put a feed through it. Okay, so we had a dead zone. We turned the feed off from there up there, and we got rid of the dead zone. So let's take a look at the data. So A, B, C, and D look like that. E, F, G, and H looks like this, except for one thing. This is a log plot here. This is linear here. So you can see that the mixing time with a good distribution of power versus tank volume is basically linear. Mixing time being linear as a function of tank volume. Over here you have mixing time as a function of tank volume, but this is non-linear, so you have a exponential mixing times an exponential tank volume. Interesting, you have the same equipment, different feed locations give rise to different mixing due to different power distributions, which give rise to different performance. It also points out that if I have a badly performing reactor, the trick would be just to change the feed location, right? In other words, this is badly performing. Change it to an external feed. Get rid of the dead zone at the top. Standard trick in the mixing industry is to change feed location. I don't know if you appreciate what that actually does for your reputation, right? You're sitting there, you walk into a reactor situation, and it's badly performing, and you tell the people to move the pipe from over here to over here, the feed pipe, move the feed pipe from here to over there, and lo and behold, the reactor turns around, does an excellent job. It certainly increases your reputation if you're into that sort of stuff. Same equipment, different feed locations, different mixing, different power distributions, and different performance. Anyway, I'm going to stop here, okay? And we'll pick this up later. And you have a good evening or good afternoon or good morning or whatever. And I hope you enjoy it. And have a good day. Bye-bye.